Hello everyone and welcome back to Thermo Shorts, where we've been talking about open systems. Now, to solve these open system problems, first we ask, what happens to the mass? Then, what happens to the energy? We'll probably have to make some assumptions about heat transfer rate and power, and then we'll have to figure out what the fluid is so that we can fix the specific enthalpy. And to do that, we'll need to know if the fluid is something like water, where we move back and forth across a vapor dome, or something like air that we can assume is an ideal gas with either constant or variable specific heat. We're going to do two examples today, and the first one is a pump. So here we're given some state information, and what a pump does is it puts in mechanical power in order to increase the pressure of a fluid. So here we're told some state information at the inlet and the outlet. The first thing that we do when we're looking at one of these open system problems is ask where our system is. So we need to draw a control volume. Then we'll do conservation of mass. Here we say the system is at steady state with one inlet and one outlet, which means the mass flow rate at the inlet is the same as at the outlet. Then we look at conservation of energy. We make a series of assumptions, and after those assumptions, we see that the power consumed by the pump is equal to the mass flow rate multiplied by the specific enthalpies at the inlet minus the outlet. Now we need to fix our states. To do that, we ask, what's the substance in the system, or what's the fluid? Here we have water coming in and water going out. Liquid water in both cases. So because we don't quite have enough information to fix both states here, we'll assume that this pump is ideal. We'll get more into what that means as we move through the course. But for now, I'll tell you that in this ideal pump, the temperature at state 1 is the same as the temperature at state 2. Now, we talked about earlier in the class that we could assume certain property values of subcooled liquids by saying that they're the same as the saturated liquid value at the same temperature. But if my temperature is the same at state 1 and state 2, I would get that my power consumed by the pump was 0. And I know that I have to plug the pump into the wall to get it to work, so that can't be right. Instead, I'll remember the definition of specific enthalpy. Now, I can say that the change in specific internal energy is 0 because the temperatures remain the same. And the change in the enthalpy is driven by the pressure change across the pump. For these subcooled liquids, we're also going to assume that the specific volume remains constant between the inlet and the outlet. So now I have this expression to find the power consumed by my ideal pump. I have some information in my state table, and it's enough to solve the problem. After I put this information into my calculator and work through my units, I find that this pump consumes negative 0.09 kilowatts. The second example we'll do today is a heat exchanger. In this heat exchanger, we have refrigerant running through a tube, and it's being heated by air that comes in at 32 degrees Celsius and leaves at 22 degrees Celsius. So the air is cooling down and transferring heat to the refrigerant. We're asked to find the mass flow rate of the refrigerant and the heat transferred from the air to the refrigerant. Again, we'll start by drawing our control volume. But that's not so simple for these heat exchangers because we've got three options. I can draw a control volume around the whole heat exchanger. Here there would be two inlets, one for air and one for the refrigerant, and two outlets. Or I can choose to draw a control volume that only includes the air side of the heat exchanger. My third option is to draw the control volume only for the refrigerant with one inlet for the refrigerant and one outlet for the refrigerant. I'll start by doing conservation of mass on the whole device. First, I assume that it's steady state, but it's not one inlet and one outlet. But I can combine the mass flow rates that are related to air and the mass flow rates that are related to the refrigerant. Since it's like Ghostbusters and we don't cross the streams here, it must mean that all the refrigerant that goes in here at state 3 must come out at state 4. And all the mass that goes in at state 1, that's air, comes out at state 2. Here I see that the mass flow rate of air at the inlet and the outlet are equal, and the same goes for the refrigerant. I would have gotten the same answer if I drew my control volumes as only air and only the refrigerant. Here I would have said that the system was at steady state with one inlet and one outlet in both cases, and I would have found that there's only one air mass flow rate and only one refrigerant mass flow rate. Next, I have to look at conservation of energy, or the first law of thermodynamics. It's a little weird when we do a heat exchanger and our control volume is the whole device, because I end up making the assumption that the system is adiabatic. Here we have to remember that these terms, Q dot and W dot and the M dot terms, they're tracking energy that crosses over the boundary of my control volume. There is heat transfer happening here, even if the heat exchanger is fully insulated. But that heat transfer from the air to the refrigerant happens inside the control volume, so it doesn't pass the boundary. So if I draw my control volume around the whole device, there's no heat transfer term in this equation after I make my assumptions. In this case, I find that m dot air times H1 minus H2 plus m dot R times H3 minus H4 is equal to 0. This equation is nice because I can manipulate it to find an expression for the refrigerant mass flow rate. This is a function of the mass flow rate of the air and all the enthalpies at the inlets and the outlets. Unfortunately, I don't know any of those things right now. To do this part of the problem, now I'm going to have to find the mass flow rate of the air using the definition of mass flow rate in the ideal gas law, and I'm going to have to fix the states of the refrigerant at the inlet and the outlet. And I used constant specific heat to find the change in the specific enthalpy of the air as it moves through the system. And after I do that, my state table looks something like this. Now I have to find the mass flow rate of the air. I was given the volumetric flow rate, and I can find the specific volume using the ideal gas law. Now I can find the mass flow rate of air. I put that into the equation that I had for the mass flow rate of the refrigerant, and I find the mass flow rate of the refrigerant. Now I can do conservation of energy not on the whole system, but on only the air side of my heat exchanger. The advantage of doing this is that I keep this heat transfer term, and that's what the problem is asking me. Now I get an expression for the heat transfer from the air to the refrigerant. Notice that my heat transfer from the air to the refrigerant is negative, which is what I expect because the air is cooling down. I can check this answer by doing the same analysis on the refrigerant side of the heat exchanger. And because I've assumed that the whole system is perfectly insulated, that means all the heat that I've lost from the air must go into the refrigerant. In other words, the answer that I'll get here will be the same magnitude, but the opposite sign, because the refrigerant has to receive all of the heat that the air lost. That's all for this episode of Thermo Shorts. I'll see you next time.